I'm back. I needed a cup of coffee. All this talking. All right, pendulum. We have two formulas for periods with pendulums. Guess where they're hidden? One is here. This was a homework assignment, I think, over Thanksgiving for you guys to learn this. And the other one's here. I see the letter K there, so that tells me this is the period of a mass sliding back and forth, okay, with a spring attached to it. This one is the period of like a pendulum that's at the bottom of a grandfather clock that just swings like this on a rope with a bob at the end, it's called. So there's my formula that relates all the things this question is relating. The period equals 2 pi square root of L over G. So let's see how they vary things here. Pendulum. So they're going to vary the acceleration due to gravity because the moon's small. Gave it the period. I want the length of the pendulum. Let's solve for a length. That would be t over 2 pi. Right, that would get that over there. Then I'd have to square that to get L over G, right? Then multiply by G, and that would give me the length of it. This is all good for Earth values. We're on the moon. So let's plug in whatever values we have. We're going to change this by saying the period was 1. I like 1. When you square it, you still get 1. Over 2 times pi is a little more than 6. 6 squared is 36, but it's a little more. Let's round that to 40. I like rounding. All times, let's see, 10. But it's not 10 on the moon, it's 10 over 6. So if I multiply 10 times 1, I get 10. 6 fours is 2240. Boom, boom. There we go. It's got to be 1 over 24 meters. I really, via escape, I really never got into this. If you look on your reference sheet, or where you get off the face of the Earth, they say that the potential energy of something way out in space, they say it's negative because, I don't even want to get into it why it's negative. I'm not even going to bother using it. But basically, you take this formula, the force of gravity equals G m1 m2 over r squared. Now, if I want to use the concept of energy here, I could say work is a change in energy of a system, right? So this thing is going to launch. It's going to shoot out into space, and eventually it's going to come far, far away where it's way far away from the gravitational pull of the Earth and come to rest. So I could say that the work done is going to be a change in kinetic energy, 1/2 mv squared. Well, if I want to go from force to work, work is force times distance. I got to multiply by the distance it is away. That means one of these cancel out. You end up with G m1 m2 over r. Multiply over by 2. I did that. Divide by m. Get rid of one of these guys, which is the thing moving, and take the square root. So velocity is going to be the square root of 2g, the mass of the planet, divided by the radius of the, how far you guys are away from each other. It says it has a radius 10 times that of Earth. So this goes up by a factor of 10. 100 times the mass. So how have you varied things? Well, that divided by that gives me 10. It's changed by the square root of 10. So there you go. All right, already went over what's going on with this one. The velocity of the mass as it passes the equilibrium position. That's where it's at its max. That's where there's no more energy in the spring. Therefore, the energy stored in the spring got converted into the energy due to motion, the kinetic energy of it. Halves cancel out. What am I solving for? V. Divide by m, you get kx squared over m equals v squared. Take the square root. Okay, they pulled it out. That would be the same as x, just x square root of k over m, and this distance, x, they say is a, so the answer is a square root of k over m. Oh, well, this is speed. Why don't we just rearrange this? Why do all the work over again? Solve that for A, you would get V over the square root of K over M equals A. All right, so simple. Oh my gosh, later I got the mass, constant of 10 centimeters per second. I got to make that meters per second. Okay, so the velocity is 0.1 meters per second divided by the square root of K, 1, I like 1, divided by 4. Well, 0.1 over the square root of, what's that, a quarter? 0.25. Square root of a quarter is 0.5. So that's like 1 over 5. That would be 0.2. Boom. This is a Atwood machine thing, where you have a big mass here, you got a little bitty mass there. Positive direction. So, let's do this the easy way, folks. It's multiple choice. Let's do the net force has to equal the total acceleration of the system times the mass of the system, or total mass. I'm going to find this because then I'll use kinematics to figure out its speed. It starts from rest. Has to, otherwise it couldn't. Oh, there we go. Starts from rest. Okay, my acceleration is going to be my net force. Tensions cancel out. You got this guy in the direction of motion. Big M G minus little m G all over M plus little m. We like to factor out the G. I don't know. I think it looks nice. M minus M G over M plus M. The difference over the sum. V naughts. Okay, so let's see. We got V initial equals 0. We got V final, which is our unknown. We know the acceleration is this whole giant thing over here. And it went a distance, h. So V final squared equals V naught squared plus 2AD. That is 0. V final equals the square root of 2 times that whole thing. D is h. I'm going to move the G over because it looks like that's what they did over here. All big M minus little m over big M plus little m. That looks like it right there, right? 2hg big M minus little. Yep. No centripetal force can do any work. The answer is 0. There is 0 work done. I like 0. Oh, here's another one. Gonna have to solve for acceleration first, which we just did. It's the difference, 3m. Gonna go this way. So that's positive. 3m minus m over 3m plus m all times g is the acceleration. So 3m minus m, that would be 2m over 4m times gravity is the acceleration. That means these guys cancel out, and it would be g over 2 is your acceleration. Now, we're going to pick this guy. I see 3's in the answers. Let me pick this guy. If I do a free body diagram, this guy, you've got tension up, and you've got 3m down. All right, so now I do a sum of the forces on that, solve for tension, use my acceleration in my expression, and I'll have my answer. So 3m minus t equals 3ma, right? Sum of the forces equals ma. Probably a little bit simpler to this guy, but whatever. That would be negative t equals, you can't cancel the m's out. You guys always want to do it because t does not have an m multiplied by it. 3ma minus, 3mg. Positive t, which is what we're solving for, go on my pen, would be 3mg minus 3ma. So that's going to equal, let's see, g, no, a happens to be g over 2. 3mg minus 3mg over 2. That equals, well, I have 3, let me see, this would be 3mg minus 3 over 2 mg's. Oops. So if I have 3 of them minus that, that would be like 9 over, nope, 6 over 2, right? Minus that would be 3 over 2, so there you go. We just answered this question. No centripetal force can do any work. Well, this is what I'm looking for here. I want to find out, I see what the potential is here. I'm looking for what the kinetic is there. Release from rest. So it has no kinetic. This is the total energy of the system. So ET equals potential plus kinetic plus heat, but hasn't come into the course yet. 3 mu naught equals, at this point, there's a little bit of both. You've got 2 mu naught for potential plus whatever the kinetic is. And we're looking for this speed. So extract this over, you get mu naught equals 1/2, let me just multiply, get rid of that, mv squared, multiply, divide by m, 2 mu naught over m, take the root, that's the speed. There you go. Bucket of water for total weight. This is my weight, which is a force, which is mg. I love constant velocity. That means there's no change in kinetic energy if this is an energy problem. And there's a distance, height, time, power required. So power is work over time, but work is the change in energy of a system over time. There was no change in kinetic because it was constant velocity, so it's totally due to mg change in height over time. mg is 50. 50 times 10 divided by 20. Last page. This is going to be good. I think there's one of these things on your midterm. I don't know. Here's my center of mass. I'm going to do all our measurements off that. You always do. All right, speed at the bottom. So this to me is an energy problem where the potential energy here gets converted into kinetic energy here. All right, so I'm going to say my mgh at that top position gets converted into 1/2 mv squared at my bottom position, which is why you don't need the mass. So the answer is just going to be 2gh square root equals v. Now, I know gravity's 10. Here's the tricky part. How high off the ground was it raised? This is not this distance. Remember, how you get there doesn't matter in energy. It is scalar stuff, not vector stuff. It is path independent. So I like the 53, meaning this one's 37. That's a 90. That makes this a 3, 4, 5 triangle. That would be 5. This would be 4 meters. And then this would have to be 3 meters. But if the whole thing was 5 meters, then it was lifted up. The difference, 2 meters times 2. So 40 squared of 40 squared of 36 is 6, so a little bit more than that. There you go. Okay, so you got, here's the shore. Doesn't need a picture for this. We need a picture for this. Student's the big mass. So we got this little board, a little mass. We got a big student with a big mass. And this guy's going towards the shore. Well, before it starts walking, the momentum of the system is 0. Therefore, whatever this guy's walking, big M, little v, to the shore with, has to equal whatever the little mass is going the other way with, big V. More than V and away from the shore. And there you have it. Good luck.